Hello students, in this lecture series we'll be discussing modern physics. The modern physics comprises of three chapters. The first chapter is dual nature of radiation and matter. In this chapter we will be discussing about the dual nature of electromagnetic waves as well as matter. That is, the electromagnetic radiations has particle nature and matter has wave nature. So in this chapter, we'll be mostly discussing about Planck's law, photoelectric effect, and de Broglie's matter waves. The next chapter in this segment is atomic physics. In this chapter, we will be discussing about the structure of atom, the radius of electron in the orbits, and the velocity of electron in the orbits, and also basically different models related to atomic structure. The Thomson model first, then the Rutherford's model, then the Bohr's model. Okay, then in the next chapter we will be discussing about nuclear physics, that is the structure of nucleus, the constituents of nucleus, and about the radioactive disintegration of unstable nucleus. And we'll be discussing about different radioactive decay laws and how radioactive substance decays into stable substances. All right, so let us start with today's lecture. So in the first chapter, that is dual nature of radiation and matter, we will see that an electromagnetic wave has both wave nature as well as particle nature. In atomic physics, we will be discussing about the properties of atom. And in nuclear physics we will be discussing about nucleus. Okay, so today we'll first start with dual nature of radiation and matter, and here first we will start with photoelectric effect. Okay, so photoelectric effect is a phenomena which is explained by the particle nature of light. Okay, and with this particle nature of light was first explained by Planck. So before we start this, we will first see an important definition, and that is what is 1 electron volt, because in this chapter predominantly we will be using the unit of energy as electron volt instead of joule. Now you know that if a charge is placed in some potential difference or electric potential difference, it will accelerate, right? So if an electron is accelerated from rest through an electric potential difference of 1 volt in vacuum, then the kinetic energy gained by the electron is called 1 electron volt. So if an electron is accelerated by 1 volt from rest, the kinetic energy gained by this electron is defined as 1 electron volt. Now the charge of 1 electron is 1.6 into 10 raised to power minus 19 in coulomb, and coulomb into volt is joule. Okay, so 1 electron volt is 1.6 into 10 raised to power minus 19 joule. Higher units of energy can be mega electron volt, giga electron volt, okay, or kilo electron volt, can be kilo electron volt. Okay, so the first thing that we have discussed before starting the chapter is defining what is 1 electron volt, because predominantly in this chapter we will be using the unit of energy in terms of electron volt, kilo electron volt, or mega electron volt depending on the situation. Okay, now next thing that we have to discuss is Planck's law or Planck's Einstein relation. So Planck was the first scientist who who postulated the particle nature of light. He said that the energy of electromagnetic radiations are carried in packets. He named these packets as quanta or photon. So one packet is one quanta, and that is called a photon. So what is a photon? Photon is nothing but a packet of energy that is carried by electromagnetic radiation. He said that the energy carried by photons are not continuous, but it has discrete values, and it can be carried in integral multiple of packets only. So the energy of one packet, that is the energy of one photon, is equal to h into f, where h is called the Planck's constant and f is the frequency of the photon or frequency of the electromagnetic wave. Okay, because see, electromagnetic waves has dual nature. So it also has wave nature, so it has wavelength, frequency, but it also has particle nature. And for means the electromagnetic radiation consists of elementary particles called photons. Okay, he also called it quanta. So the energy of one such photon is equal to hf. This is Planck's law. So if there are n number of photons, then you will say that the total energy is equal to Ne. Total energy is represented by Q, and Q is equal to Ne, and E is HF. So because the energy is discrete, you cannot have 1.5 packet of energy or half packet of energy. You cannot have any energy between HF and 2HF. You will always have an integral multiple of energy of one packet. Okay. So now E is equal to HF. Now F can also be written as C by lambda, because you know that wave velocity in case of radiation is c, that is the speed of light, and c is equal to lambda f. So you will write f is equal to c by lambda. So you can here replace f with c by lambda, then you will write the energy of one photon is equal to hc by lambda, where h is this Planck's constant and the value of Planck's constant is 6.626 into 10 raised to power minus 34 joule second. But because in this chapter we'll mostly use the energy in terms of electron volt, that is why we will write this joule in terms of electron volt. Now 1 electron volt is 1.6 into 10 raised to power minus 19 joule. So 1 joule is 1 divided by 1.6 into 10 raised to power minus 19 electron volt. So this 1 joule can be replaced as 1 by 1.6 into 10 raised to power minus 19 electron volt. Okay. Now if you divide this, you will get H is equal to 4.14 into 10 raised to the power minus 15 electron volt second. So this is the value of H in terms of electron volt second. Now H is a constant, a universal constant. C is also a constant, the speed of light in a vacuum, and the product of H and C will also be a constant. Now we will remember the value of product of H and C. So the product of H and C is nearly equal to 1240 electron volt nanometer. So remember the units also. Hc is equal to 1240 in electron volt and nanometer, and it will be 12400 electron volt angstrom. So 1240 electron volt nanometer, and here 12400 electron volt angstrom. Okay, so the Planck's law is describing the particle nature of light, and it is saying you that the energy is discrete and it is not continuous. Energy is carried in packets, and you cannot have means you can only have an integral number of or integral value of packets. Okay, you cannot have energy between the two packets. Okay, now let us discuss some properties of photons. Now a photon is an elementary particle which comprises the electromagnetic radiation. So basically electromagnetic radiation is nothing but collection of particles, elementary particles called photons. Photon is the quantum of electromagnetic radiation. So we have already discussed what is one quantum. The definition of quanta, the word quanta means it is the smallest discrete amount of anything. So one quantum of electromagnetic energy is called a photon. So the plural of quantum is called quanta. Now photons, or in general any electromagnetic radiation, has oscillating electric and magnetic fields. So the energy is stored in this oscillating electric and magnetic field. So photons are nothing but these electric and magnetic fields which are traveling through space. Okay. Photons are neutral, that means it does not have any charge. It does not have any rest mass. So it does not have any rest mass. It can have, it means it has moving mass, but it does not have rest mass. Now what does this mean is, listen carefully, photons does not have rest mass means that a photon can never be at rest. You can never find a photon which is at rest. Now in general, for any matter, be it photon or any other matter, moving mass is always different from rest mass. Now, what is moving mass? Moving mass is equal to rest mass divided by under root 1 minus v square by c square. That means moving mass is always greater than rest mass. Moving mass is always greater than rest mass. Okay. Now, if rest mass is non-zero, so for any matter, you know that rest mass is always there. So if rest mass is non-zero, in that case, you will say that we can never attain the speed of light. Why? Because if we have attained the speed of light, that means c by c becomes 1, 1 minus 1 becomes 0, anything by 0 is infinity, that means the moving mass becomes infinite. Mass cannot become infinite. That is why if a particle has some rest mass, it can never attain speed of light. Photons can attain speed of light because it does not have rest mass. Okay, so photons does not have rest mass, but it has moving mass. Okay, photons travel at a speed of light that we have already discussed. Now, how are these photons generated? Photons can be generated by numerous methods. Okay, we have discussed in electrostatics that an accelerating charge produces electromagnetic radiation. So photons are emitted by the action of charged particles, although they can be emitted by other methods including radioactive decay. So in the third chapter of this module, that is nucleus, we will study nuclear decay or the radioactive decay. In that we will see that gamma rays or electromagnetic radiations can be emitted during radioactive decay. Okay, now since they are extremely small particles, the contribution of wave-like characteristics to the behavior of photons is significant. Means this we will actually understand when we study the de Broglie's hypothesis. So de Broglie, or actually means in actual pronunciation, de Broglie is said as de Broglie because his name is pronounced as de Broglie. So de Broglie stated that uh, we will discuss that later when we will study de Broglie equation. Okay, so uh, the next point is photons are often described as energy packets. Now, this we have already discussed. The photons are nothing but energy packets. This is a very fitting analogy as a photon contains energy that cannot be divided. You know that photons energy cannot be divided. This energy is stored in the oscillating electric field. These packets of energy can be transmitted over vast distances with no decay in either speed or energy. So now you know that photons carry energy. Okay, but it also carries momentum. Now, how to find the momentum of a photon? The momentum of a photon is found out using the famous Einstein's mass energy equivalence relation, that is E is equal to mc square, where m is moving mass of any matter. So here what we will say, m is for a photon, m is moving mass of the photon is equal to energy of the photon divided by c square. You know that energy is hf, so it is equal to hf by c square, right? So the momentum of a photon is equal to the moving mass of the photon multiplied by the speed of the photon. The speed of photon is the speed of light. So m is equal to e by c square multiplied by c, that is e by c. Okay, now momentum is equal to e by c, and e can be written as hf by c, or hf can also be written as hc by lambda by c. So the momentum of a photon is equal to
E by C, and that is also equal to h by lambda. So you have to remember the formula for momentum of photon, and obviously also the Planck's relation, that is the energy of a photon. Okay, so this much momentum is carried by the photon. Now if photon carries momentum, then this means that it will also exert force on a wall when it strikes a wall. Okay, but we'll discuss that later. Okay, now the first thing that we'll discuss in this chapter, that is wave particle dual nature, okay, is the photoelectric effect. Now at that time, when this phenomena was discovered, scientists were very puzzled, because at that time we knew that electromagnetic radiations are waves. Okay, but any wave property could not explain why is photoelectric effect occurring. Okay, or what are the means, what the observations that we were getting was not explained by the wave nature of light. So in that case, in that situation, Planck discovered, or Planck postulated, the particle theory of light, and he said that particle means photons, or you can say electromagnetic radiations, are nothing but collection of elementary particles called photons. Okay, now first let us see what is the definition of photoelectric effect. So when electrons when light of sufficient frequency strikes a metal surface. So light of sufficient frequency strikes a metal surface. Electrons are ejected from the surface. Okay, and this phenomena is called photoelectric effect. So it's a very simple phenomena where when light of sufficient energy is striking a metal plate or any photosensitive material, then electrons are getting ejected from that material. This phenomena is called photoelectric effect, and the ejected electrons are called photoelectrons. And if you complete this circuit, then this electron will move like this, and the current will be opposite to the flow of electron, and you will say this is photocurrent. So this is called photocurrent. Now the plate from which the electrons are ejected are also called emitter plate, right? Emitter plate, we also call it as cathode. And the plate in which these electrons are getting collected is called collector plate. Okay, we also call it anode. Okay, now for going into the details of photoelectric effect, we must first understand some definitions. So the first definition is accelerating voltage. Now what is accelerating voltage? See, this electron, if you want to accelerate this electron which has ejected from this metal, what you have to do is you have to give it a force, right? So to give it a force, there has to be some electric field. Now because it is a negative charge, so the field has to be, or the force is opposite to the field. So if you want to give it a force towards the right, the field has to be towards the left, right? Only then it will accelerate, right? If the force is towards right, so the field has to be towards the left. Now you also know that electric field always points from high potential to low potential. So to generate an electric field in this direction, there has to be a potential difference where this has to be the higher potential and this has to be the lower potential. The general convention is that we take this potential as zero. You know that potential is a relative term. So absolute value of potential actually does not have any meaning. So if you take this as zero, then this has to be positive, right? If you take this as zero, this has to be positive. So you will say that this electron will accelerate if this has a positive potential with respect to this. So that means accelerating voltage is defined as the positive potential of the collector plate, that is the anode, with respect to the emitter plate is called accelerating potential. So in this situation, the speed of the electron will increase, right? So what is accelerating voltage again? The positive potential of the collector plate that is the anode, this is the anode with respect to the cathode. So that means if this is 0, this has to be positive, or you can say the difference between this and this has to be positive. Okay, so in that case you will say that this potential is accelerating potential or accelerating voltage. Voltage means potential difference basically. Okay, so in this situation the speed of this electron will increase. The next definition is retarding voltage. Now what is retarding voltage? So let us see what is retarding voltage. Now if you want to decrease the speed of this electron, okay, if you want to decrease the speed of this electron, in that case what you will have to do is you have to get a force in this direction. Now to get a force in this direction, the field has to be in this direction. Now to have a field in this direction, there has to be a potential difference wherein this should have the higher potential and this should have the lower potential. Now by general convention, we take this potential as 0. Now if this is 0, then, and this is the higher potential, in that case this will be the negative voltage with respect to this. So you will say you will define the retarding voltage as the negative voltage or the negative potential of the anode. Anode means basically the collector plate. So this time this has the lower potential with respect to this. So the negative potential of the collector plate with respect to the emitter plate is called retarding potential. So in this case the speed will decrease. The next definition is stopping potential. Now what is stopping potential? So the retarding potential which stops the most energetic electron from reaching the anode is called stopping potential. So what does this mean is you want that there should be no photocurrent. If there is no photocurrent, that means electron should not reach from here to here. So that means the electron must slow down, slow down, slow down, slow down, and by the time it reaches here, actually it should not reach here. It should stop before this plate. So if electrons stop here, then electrons will not reach this collector plate and there will be no flow of electrons. Okay, so that means the retarding potential which is so high, the retarding potential which is so high S2. Now retarding potential, focus on retarding potential. Retarding potential means that it should slow down. So it should slow down up to that extent such that it is unable to reach this. Okay, so now one more thing is important here is these electrons which are coming out have random kinetic energy. But there is one term called the maximum kinetic energy or the most energetic electron. Now, if you are able to stop the most energetic electron from reaching here, then obviously all other electrons will not be able to reach here. So that is why we have defined the stopping potential as the retarding potential, which stops the most energetic electron from reaching the anode, is called stopping potential. So in this case, you will say that the photocurrent becomes 0. Okay. So retarding potential which will not allow the electron to reach the collector plate is called the stopping potential. The next important definition is work function. Now what is work function? See, it is the minimum energy of the incident photon which can eject photoelectron from the metal surface, or you can say which can cause photoelectric effect. Now what does this mean is, suppose you have this emitter plate or the metal plate and energy is incident on it, or you can say photon is incident on it, right? Now if a photon is incident on it, then electron will be ejected only if this energy is greater than or equal to the work function of the metal. The work function is the minimum energy that is required by this metal to show the phenomena of photoelectric effect. If this energy, that is the incident energy, is less than the work function, then there will be no photoelectric effect. Okay, now this work function of a metal is a property of the metal. It depends on the type of metal, but it is independent of the incident light. Whatever light you incident, if the metal is lithium, its work function is fixed. Now, you know that the photoelectric effect involves the ejection of electrons from the atoms and then subsequently through the surface. Okay, first electrons are ejecting from the atoms and then from the surface as a whole. Okay, so now to eject the electron from the atom, you need how much amount of energy? That is called the ionization energy, right? So the work function of the metal, which is represented by the phi or W, is dependent on the ionization energy of the metal. Now in your NCERT textbook, the work function of different metals are given. Now you don't have to remember it, but actually they can ask you comparison of this work function of different metals. So you should at least remember which has the maximum work function and which has the minimum work function. Okay, so you can write it in your notes, the work function of different metal from your NCERT textbook. So that part is homework for all of you. Okay, now the next definition is called the threshold frequency, F naught or nu naught, and the threshold wavelength lambda naught. Now frequency is sometimes written as f or nu. Okay. Now what is threshold frequency? It is the minimum frequency of the incident photon which can eject photoelectron, or you can say which can show photoelectric effect. So the work function is the minimum energy and f naught is the minimum frequency. So definitely phi has to be equal to hf naught. Okay. Similarly, now you know that E is equal to hc by lambda. That means E is inversely proportional to lambda. That means more the wavelength, less the energy, right? So that is why threshold wavelength is defined as the maximum wavelength of the incident photon, the maximum wavelength of the incident photon which can eject photoelectrons. Okay, so the maximum wavelength of the incident photon which can eject photoelectron is called the threshold wavelength. So you will say phi is equal to hc by lambda naught. So therefore we make a conclusion that if the energy of the incident photon is less than phi, or the frequency of the incident photon is less than threshold frequency, or the wavelength of the incident photon is greater than the threshold wavelength, then you will say there is no photoelectric effect. If energy is greater than phi, or the frequency is greater than the threshold frequency, or the wavelength is less than the threshold wavelength, then you will say that the photoelectric effect may occur. I'm saying may occur because the efficiency is very less. That means if crores of photons strikes the metal plate, only a fraction or a few number of electrons will come out, right? So that is why I have written may occur, because it's not necessary that even if the energy is sufficient, electron is getting ejected. It's not necessary. All right. Now, the next important point is the kinetic energy of the ejected electrons. So, I have already told you before that the electrons that are coming out is not having a means constant or same kinetic energy. All the electrons, crores of electrons are coming out, and all these electrons have random kinetic energy, but this kinetic energy is anywhere between 0 to KEmax. The kinetic energy is random, but it is not going up to infinity. It has a limit, and that limit is called the maximum kinetic energy, represented by KEmax. Okay, now if you draw the graph between the number of electrons and kinetic energy, you will see that this kinetic energy, this much number of electrons are present. This kinetic energy, this much number of electrons are present. That means it's completely random. Every kinetic energy is there with some of the electrons, because the electrons are in crores, numbers are huge, right? So if the numbers are huge, every electron is having different velocity. So this particular kinetic energy is possessed by this much number of electrons. This kinetic energy is possessed by the maximum number of electrons. Okay, so this is the maximum kinetic energy. You cannot have a kinetic energy beyond this. This is the limit. The kinetic energy of the ejected electrons can be anywhere between 0 to this. Okay, so I have drawn it like this because hardly any electron will be there which is coming out with KEmax. So that is why I have shown here KEmax to be 0. Means this KEmax, at KEmax the number of electrons becomes 0. Okay. Now why is the kinetic energy of all the electrons that are ejecting are different? They are different because once they eject from the atom, once they eject from the atom, they have to come out of the surface, right? This kinetic energy is calculated from the surface, right? So when they come out of the surface, they will undergo multiple collisions, okay, with other electrons, with atoms, okay, with any other particles. So due to these collisions, what will happen is it will lose energy. So that is why before coming out, it loses huge amount of energy, and that is why it cannot come out with Kmax. Okay, the electrons from an atom will collide with other electrons and other atoms before coming out of the surface. In this process, it will lose energy. Now, one more thing that is uh, we have to think here is what is this KEmax and how we will calculate the maximum kinetic energy, and what is the significance of this maximum kinetic energy. Now, you know that energy in every system is always conserved, right? So this simple phenomena of conservation of energy was used by Einstein to find the Einstein's photoelectric equation. Now, what is this? So, if E amount of energy is given to a metal plate, out of this E amount of energy, phi amount of energy, that is the work function, is utilized to overcome it. So suppose you have 100 mangoes and you have given 80 mangoes to your friend, then 20 mangoes still remain with you, right? So in the same way here, E amount of energy is given to the plate, right? Out of this, phi is required to overcome the work function. The remaining amount of energy gets converted into the kinetic energy of the electrons. Okay, so the remaining amount of energy is the kinetic energy of the electrons. Okay, this relation is called Einstein's photoelectric effect equation. Okay, so this is the maximum possible value of kinetic energy. But yes, electrons are not coming out with Kmax. It is coming out with an energy which is much less than Kmax. Okay, we are just finding the limit up to which the kinetic energy can be possible. Okay, now what is the relation? Now one more thing that we have to discuss here is what is the relation between this Kmax and the stopping potential. Okay, now you know that if an electron is accelerated by 1 volt, it gains 1 electron volt. Similarly, if an electron is retarded by 1 volt, it will lose 1 electron volt. Now, stopping potential is what? It is losing Kmax from Kmax to 0, right? So you know that 1 volt of retarding potential will, or you can say X volt of retarding potential will cause a decrement in energy of X electron volt, right? So X volt of retarding potential will decrease the kinetic energy by X electron volt. So here you want to decrease the kinetic energy, means from Kmax to 0. So you will write Kmax minus 0 is equal to EVS, because stopping potential is that potential which makes the kinetic energy from Kmax to 0. So EVS is equal to KEmax. So this is the relation between stopping potential and KEmax, and this is a very useful relation and a very easy one that in the question, suppose it is given to you that the stopping potential is x volt. That means they have actually given you the kinetic energy maximum value. The kinetic energy maximum value will be x electron volt. So if the stopping potential is x volt, the maximum kinetic energy is x electron volt. It's so simple. Okay.
If you like my video, do hit the like button and share my work with your friends, your juniors, your seniors, and any other student who is preparing for JEE, NEET, and any other competitive exam. Also, subscribe to my channel and hit the bell icon so that you get notified whenever I upload my next video.